Well, good afternoon, everybody. Thanks for coming. I know it's always a little hard, last day of the conference, after lunch, to just push through those last few talks. Really grateful that you're able to make this one. I hope it's going to be good. Let me give you some context into what's informing this talk. As Dixon was explaining, in my role at Databricks, I'm exposed to a bunch of problems that our customers and people interested in using Spark for machine learning applications run into. And a lot of the times, I realize that the root of the problem is a poor foundation of understanding how to design experiments for machine learning. So what I'd like to do is start by discussing some problems in modeling and how we might want to think about what we can do to build experiments to solve some of these problems. So the first problem, and actually the second problem, share the same type of start. So we have a known business problem. We've defined it. We know that machine learning is a candidate solution. And in the first problem, let's say we've selected an algorithm and it's been implemented. And the question we want to answer is, what is the expected generalization error? And how do we go to our business and tell them and give them confidence in these model results? The second business problem is a little bit different. Let's say we've got a few different approaches and we're trying to decide which one to choose. Maybe we want to know which approach has the least amount of error due to generalization. Let's talk about two more. So the start is a little bit different in problem 3. So we've got a business problem that we've already solved with a machine learning model. So this happens a lot of times where if you have customers coming from a single node framework or they've been working with little data and they're starting to scale their machine learning up to larger data sets, and it's not going to scale. The model as they've designed it will not scale. So they have to develop a parallel model or a distributed model, and it has to be designed and tested. The fourth problem is, again, we've solved a business problem with a machine learning model. We want to know how changes in the input are going to affect the output and the types of predictions, inference that we make from the model. And then finally, what happens to our model after we retrain it? So I want to start this by talking about what a machine learning study looks like to me. And again, this is informed by seeing this happen where we start too quickly. We don't start with the fundamentals. And when I think about a lot of the audience is most likely familiar with machine learning principles, so I'm going to go over this quickly. But I like to start with really understanding the business problem, the types of factors, constraints that are going to affect what the input data set might be, what the output data set might be, how does the business think about the problem, how are they going to assess outcomes, really understanding the problem and planning a study. And planning a study is really important because it's going to inform the types of model that you might build or how you will start creating and designing an experiment. And this process is referred to as conceptual modeling, and this is probably the most fundamental component of this entire study. Because if your conceptual model is poor, when you actually get into the modeling stage where you are testing different algorithms, you're trying to collect some metrics about the model performance, you're not going to be able to use any of the model because you have a poor basis by which to build your model. So included in this step are activities like getting the data, mining insights from it, and having a loose idea of the type of model that you're building. So for example, is this going to be a supervised model? Is it an unsupervised model? How quickly are we going to train or retrain? Those types of things. And I like to encourage that once you have formed a conceptual model, really try and assess its validity. And this is really important when conceptualizing a distributed model because it's different between a single node framework versus a distributed framework. And the key thing is that some algorithms are not going to have a distributed implementation. So dbScan is a good example where the computational complexity of this algorithm as it is distributed is it's not appropriate for, I think it's the number of rows to the 4/3. And that is not going to scale well in a distributed setting. So if your existing machine learning model uses dbScan, you may need to evaluate other algorithms to use. And really understanding computational complexity is very important, and we'll talk about how that is a part of the experimental design process. In addition to the algorithm, the solvers and the optimizers often have different implementations. So what that means is even if you're using the same algorithm, the underlying optimizer may act in a different way. So if you're used to conducting experiments where you have the same input set, you have the same model, you set your seed, so you've handled any stochasticity, you expect the outcomes to be the same. Sometimes that's not going to be the case when you're first getting started with using some of these distributed algorithms because they have different implementations. And again, sometimes when you're migrating from a serial environment to a distributed environment, you may break some of your assumptions without realizing. So it's really important when you're going through that conceptual modeling phase to think about all these things. In addition, let's talk about the challenges of big data very quickly. Obviously, when you have more data, it's more likely that you're going to see outliers. And this is really significant because we often see that they're incorrectly or poorly modeled. And if you do things like missing value compensation, it can actually have a greater significance in the skew that's introduced as you scale out your data set. So this is, again, coming back to the assumptions. And synthetic data is usually a poor representation of an actual system. So an example that I use is if you're trying to build a predictive disease model, you shouldn't use synthetic data to model an observation of a rare disease because oftentimes the synthetic data is markedly different than the actual system we're trying to represent. And going back to this idea that when we move from a serial framework into a distributed framework, I like to start by talking about the way that scale out is implemented in a distributed setting. So this diagram that you're seeing refers to scale out. When I say scale out, I mean a model scaling out with the size of the data. So there's two types of parallelism broadly. The first is embarrassingly parallel. So this is basically maybe you have a random forest model and you have 100 trees and you want to train a single tree on a single node. So if you have 100 nodes, you should expect in one pass you've trained every single one of your trees. So that would be an embarrassingly parallel application. The second is scaling out, and this is where we have a data set where the algorithm requires certain statistics, metadata about the entire data set in order to be mathematically robust. And so this is very canonical Spark, right? We're breaking our input data set into partitions, but the key thing here is that when we ship those partitions out to executors, they're actually performing a bunch of aggregations and statistics on that local partition. So portions of the algorithm are computed or certain steps are executed, and then communication happens back to the driver. So the really important thing that I want you to notice here is that the executors are communicating back and forth to the driver multiple times. And this is called distributed model execution. So what you may see when you're writing a Spark job is that there are multiple Spark jobs actually occurring for a single evaluation of or training of a machine learning model. So now that we've got our conceptual model, let's talk about building a learning model. So critical to machine learning is the ability that we can define a model that can learn as we use more and more data to as our input to this model. So this is where most of the machine learning that we've seen in the field really starts, where you say, okay, I want to build a k-means model, and now I need to tune the parameters and do hyperparameter tuning and those types of things. This is usually the more established because you have to have this part. It's definitely really important. Again, we like to say it's important before you start moving your model into production, thinking about, is this learning model valid? And this is where most people are familiar with experimental design. So one way that you might want to assess your model's validity is by looking at the number of false positives or something like that, or measure accuracy or things like that. We'll talk about how you can do that a little bit more robustly. So once you have a valid learning model, you can go into experimental design or experimentation. So this is where you do things like design experiments. We'll talk about what an experiment is. You'll evaluate this learning model, and this is typically in sort of a pseudo-production setting. You'll analyze that output data, and then you'll present the results of your model, launch it to an application, monitor it, maintain it, all those production things. This is actually the focus of this talk, is really this experimentation phase. And really, the goal when we're talking about experimentation is to understand the effect that model factors are going to have on the model and obtain conclusions that are statistically significant. So statistically significant is very important because that is going to help us come back to our organization and assign confidence to the claims that we make about our model's performance. And this is really challenging for distributed learning. So when we talk about designing an experiment, we want to have some way to manipulate the factors that we have control over and collect responses and then do something with those responses. And statistical methodology gives us a bunch of ways to understand and build ways to use those responses to obtain conclusions about our model's performance. So an experiment needs to be independent. So that means that you have isolated it for any sorts of dependencies that can be introduced. It should be controlled for variance and uncontrollable error. And we'll talk about what that means. When I say uncontrollable error, it means something that I'm not actually using as an input to my model, but it's present in the system. And it should be reproducible. This is really important because we want to treat this discipline as a scientific discipline, so it should be reproducible, or at least we should have a methodology for getting reproducible results. So when I talk about the ability to have a reproducible model, some of you may be thinking, well, a lot of these algorithms and optimizers use stochastic principles. So are we setting seeds? Is that what we're thinking about? Well, that may be it, but it may also be understanding how many times we need to evaluate our model sort of independently so that we can have broader claims about, the average types of generalization error or the variance of the generalization error. And some of the things we'll talk about that help do that is measuring classifier performance and hypothesis testing. So just so we're clear, when we talk about model factors, there are two types, controllable and uncontrollable. Controllable ones are the types of algorithm that you're using, the input data, any set of parameters, hyperparameters, or model parameters that you're using. And uncontrollable things mostly have to do with data or randomness. So if you're using or if you're seeing noise in the data, this is new data coming in, that's going to be uncontrollable. And anything that you didn't observe during that training process is usually considered uncontrollable. So now that we have let's just assume we have a machine learning model and we need to start designing an experiment. We have to actually generate some responses. And when you are working with optimizers and solvers in any sort of machine learning framework, you have to think about, have I chosen my model parameters correctly? Have I designed my controllable factors correctly? And so there are generally three techniques for changing factors to get various responses to understand and answer some of those business problems we looked at earlier. Under each of these graphs, you'll see a little complexity graph or complexity result here. This is really important because obviously the graph on the right, which is called grid search, is the most robust because you've absolutely spanned the parameter space of these, in this case, two factors, right? But the complexity of doing that type of response search is potentially very high, and F here is the number of factors. So if you have 100 factors, your computational cost to doing that type of exhaustive search is very high. It's often untenably high. The other two choices are sometimes appropriate. Maybe the first type of situation may be informed by feedback from subject matter experts. The second is when you have isolated maybe one or a few factors that are really subject to the most variability in the response. So maybe you want to fix 70% of the factors and you want to do a more exhaustive search on 30% of the factors. So these are some of the ways that you can think about generating responses and strategies to generate those responses. So let's actually jump into the API and talk about how you do that. Now for sort of an ad hoc search, You actually have to use param maps in MLlib. So we'll see a code snippet here. And basically what you do, and we'll look at this in the next slide, is you pass that parameter map into a way to gather those responses. In the second graph, in the third graph, we're basically building a grid using a grid building technique inside of MLlib. And basically what's happening is all the combinatorics are being done in the background. So in that third graph, we have two factors, and we just find all the combination of the factor choices that we've given. So once we have our factors chosen, we can actually generate responses. In MLlib, we have two options for that. The first is a train validation split. And this is going to create an estimator. So that estimator is actually, it's an estimator of the generalization error, or in this case, the actual responses for maybe predictions against labels if you're training a classifier. It's going to randomly split the data set into whatever ratio you supply. And it's going to use the evaluation metric to select the best model. So in this case, what we're doing is we're passing in that factor grid. So that factor grid can also be a single parameter if you want. And we basically evaluate the model. And then once we have our model, we basically use that train validation object to fit it against some test data. We can get a model and extract the parameters from that model. And this is in the case that maybe we're testing multiple models, right? But the key here is that we're really only splitting the data once. And this is going to factor into our complexity in runtime. And another thing that's important here is whenever you're evaluating a given model, and this comes back to the differences between single node frameworks versus distributed frameworks, different models have different types of metrics and methods within those models. So if you're thinking about in the conceptual modeling phase that you want to use a support vector machine to solve this problem, you really should go look at the API beforehand and see what types of statistics you have access to once the model has completed. So logistic regression is going to have more metadata for you to use later in your experimentation phase, and that's a really critical component. So let's talk about the cross-validator. This is probably what most people are familiar with during this phase. The key difference here is that we're setting a number of folds. And the nice thing about this is it's going to control for some of the variance that can happen during model selection. So when you're selecting a model, you can fall into the trap where your validation set or the set that you're using to perform model selection has some characteristics that's going to bias one model over another. So when you use cross-validation, it's going to help control for that. So this is, again, how we're going to control for those types of factors. And these are, in this case, uncontrollable factors, because if you have noisy data or observations that you didn't train your model on, you're going to see that. It's going to show up in your cross-validation responses. And when you perform cross-validation, so in this case for the Spark APIs, I mean, I've now created a cross-validation object. I've fit it to the test data set. That model has an object called best model, and that's a really important thing. It's actually the selected model that has the highest average from cross-validation. And from it, you can get a bunch of metadata, including the best parameters that resulted in that model that's selected. So in this case, it's really important that your evaluator, in this case, I'm using a binary classification evaluator, is chosen correctly, or else your selection from cross-validation may be unexpected. So throughout this process, sometimes the response we get from customers is, wow, this takes a long time. And yeah, that's true. Because if you're dealing with hundreds of millions of rows or billions of rows, and it takes you 2 hours to train one model, and you want to control for a bunch of factors, so that means you're maybe evaluating 30 models, you can imagine how this becomes very complex. And this is, again, where we come back to the importance of the conceptual model. If your conceptual model is really well formed, this will inform the factor choices that you make when you're trying to generate responses, and it's going to reduce the number of iterations your model has to go through. Sometimes you can do things like factor normalization. So a lot of times we see customers that are confused by parameters or hyperparameters in the MLlib models themselves. And what we typically guide them on doing is actually using the data set, so having like a first pass over the data set to inform or normalize the factors that you use as inputs to those MLlib models. And we kind of talked about a little bit about how cross-validation can also be used to limit the number of responses. So when you do cross-validation, you're splitting the data into typically K partitions. And that can be nice because you don't have to train your data or your model on the entire data set. Okay, so let's talk about analyzing model output. Typically, I like to focus on classification and regression. So you'll notice a little side thing on regression there. Regression is really easy when it's linear, and it's really hard when it's nonlinear. So let's really focus on classification. So for classification, typically we're thinking about looking at the number of positive and negative responses from a typically binary response. So if you notice on the lower right-hand corner, this is an error function. It helps us understand and assess a given outcome as being, correct or incorrect. This is typically a binary outcome, but it doesn't always have to be a binary outcome. One of the limitations you're going to find in distributed packages like MLlib is that you're really limited to these type of binary error functions, which is a limitation. So obviously, when you have a binary classification, it's a lot easier to think about the relationship between precision and recall. We have a lot more that we can use to inform our modeling model selection process. Typically, we're talking about the receiver operating characteristic curve. It's very popular. When we're talking about multiple classes, most problems in practice are multi-class. The best tool we have is confusion matrix, and we'll look at that in a little bit. And for multi-label classification, we're actually not going to spend a lot of time talking about that, but MLlib does support lots of techniques for multi-label classification, and the ones you're going to want to look at are measures by label. So, the example that I use is if you're thinking about, modeling the MNIST data set, just as a very basic example, right? You can train a classifier that is going to classify every single label at the same model. You may want to think about strategies to maybe look at a single label, or if you're training a classifier on this problem, you may want to look at measures by a single label. All right, so let's talk about binary classification. So you can see in this case how I'm building a metrics object. What I want to point you to here is some people say, well, hey, wait a second, isn't that the MLlib API? And it actually is, and you can use it for, you should use it for analyzing model output, even if your model is trained using the later ML or data frames API inside of MLlib. So you can see that I'm just basically mapping the data frame into something that can be input into, or turning it into the right input format for the binary classification metrics class. And that's going to give us access to all these types of metrics that you're seeing. So these are only a subset of ones. I just wanted to highlight some. If you're thinking about assessing this binary classifier, obviously you have your area under various curves. I also want to point out measures by threshold. These can be really important. So threshold curves are really nice if you want something that's a little bit different than just area under the curve. So you can define thresholds by measure. So in this case, what I've done is I've taken recall precision and then the F measure. In this case, this is the F1 measure, and I can simply capture those the metrics and basically join them all onto the thresholds and plot them. And this will give me a bigger picture of how the model is performing based on the relationship between recall, precision, and F measure. So let's talk about multi-class. We have multi-class metrics that are really helpful. Obviously, basically, it's the same type of formulation to get access to these metrics. We're going to talk about confusion matrix. I want to talk about accuracy for a second. Accuracy is usually not a robust metric by itself. It's usually good during that learning model phase when you're not worried about being robust. You just want throw something against the wall, get a sense of how this model performs. We also have measures by label and weighted measures. So let's talk about the confusion matrix. This is obviously the most popular. We get asked all the time, how do you plot a confusion matrix inside of Databricks? And we actually tell you to go use some sort of third-party package because, Python or R are much better for this than Scala. So, what the confusion matrix is doing is it's actually looking at the way that a given class is classified. So, if a class has a label 1 and it's correctly classified, or anything that's correctly classified is run along the main diagonal. And then you can see in this case, in the lower left-hand corner, that the label that was that the true label was different than the predicted label. So in this case, it was truly, or the true label was 2, and it was classified as a 0. So if we notice like a hotspot in this confusion matrix, we know that we need to tune our model in that particular location. So let's talk about hypothesis testing. Hypothesis testing is really important because you can figure out if your model's correct. And it's going to define the significance of your result. It gives you a mechanism to going back to your business and putting together a report that says, I know what I'm talking about. You can trust this model. Don't worry about factors about this model being uncontrollable because I put together this battery of tests. And there's typically 2 types of tests that I like to talk about. So the first is, how likely will my model misclassify, or maybe is the regression error significantly different than the observed or the true result. And then the second is, if I have 2 learning algorithms, how do I select or which one has the lower expected error rate? And so if you notice on the right-hand corner, I've got a few tests that you can use, and I've classified them as the type of problem or question it would be solving. So let's actually look at a few. So I want to talk about the chi-squared test. This is new in Spark 2.2. And the hypothesis that this is testing against is, are our outcomes statistically independent? And this is true for one given model. So this is going to basically evaluate an independence test for every feature against the label that's defined. And we basically compute feature label pairs. But this is only going to work for categorical. And so you can see basically what I'm doing is I am passing either my labels or my contingency matrix into this test. And then I can print a summary. This summary becomes more and more complicated depending on the dimensionality of that matrix. But this is really useful. However, this isn't the end of the story, right? This is only one such test. So one of the things that I'm not going to spend too much time talking about here, but you'll see, is that really you have to create a battery of tests. There is no one silver bullet test. Your model is only so good as the assumptions that you use, your data, and the types of testing that you come back with. So another test that you can do, and this is a very simple test actually, is called McNemar's test. And it's basically testing whether or not 2 models have the same generalization error. So you can see the formulation on the right here. You can basically find whatever test you want. So create your hypothesis and find out what types of information you need from your labels to compute your test. So there are many, many tests that you can use. And this is where having an understanding of statistics is really important when trying to build and select these hypothesis tests. The last thing I want to talk about is analysis of variance. There is a way to do analysis of variance inside MLlib, but it requires manually calculating various statistics. And this is really useful, except we don't have a mechanism out of the box to do this right now. So what I typically recommend for people wanting to do analysis of variance is make multiple runs of a test and basically do it offline. So it's usually easier than having to go in and add those and collect those statistics during runtime, because you actually have to extend the MLlib class that you're running, which can be challenging. All right, thank you very much. Any questions?
If you guys have any questions, feel free to step up to the mics on the left or the right.
Thanks very much for this nice presentation. So I have a couple of questions. I hope you have time. The first question is there any support for Bayesian hyperparameter search in Spark?
That's a good question. Can you explain like what type of methodology you're using?
Well, actually, the Bayesian hyperparameter search is when you actually start somehow, not very random, not very grid search. So it actually learns what kind of combinations of hyperparameters had the best result in the previous run. So it actually kind of directs the direction of the search, in your hyperparameter space.
I'm not sure. I know we do have a suite of tests for Bayesian methods specifically. I don't know if we have that.
Okay.
So we can talk after about that.
Okay, great. So the next question is whether Spark supports continuous learning. Let's assume that I have a model. I trained it on the past, let's say, 3 months of data. Mm-hmm. When the new snapshot of this week's data comes actually in, is there any way that I don't need to actually to train or retrain my model on the whole data? I just update my model based on the new snapshots of the week or anything?
Yeah, so Spark does not currently support those types of models.
Okay, thanks very much.
Thank you. Any other questions?
Thank you for the presentation. I saw in this talk and a few other ones that it was several references to MLlib. Is there a distinction between ML and MLlib, or is that MLlib is going to phase out, or is it not going?
Yeah, that's a good question. Actually, so Spark.ml, which is one of the machine learning namespaces, is part of MLlib. So they're really just different namespaces. They're all part of the same package. So if you're talking about the namespace Spark.mllib, it's not going away. We haven't had consolidation yet, like we have in the rest of for example, Spark SQL. So we anticipate supporting MLlib and the community supporting MLlib for the foreseeable future. And part of the reason is we have access to so many great classes and useful utilities that it's really not on the roadmap to move away from it.
Thank you. We have time for maybe one more question.
My question is that I see there's some measurements for how good your model is, like the area and the curve. But is there also some possibilities for, because these are overall measurements, and I work a lot for marketing, direct marketing campaigns. So I'm more interested how good the best model is on the best 20% of the population. Do you have also these kind of measurements? Or?
Yeah, so that sounds like you're making an assumption about the population that you're trying to model. Yeah. Is that right? So you're selecting a subset, and you would probably need to separately assert the claim that this population that you've selected is representative of the broader population.
I don't know if that's the...
So maybe I misunderstood your question.
So, like, I work for a telco, so we have all the... Our customers are like 1 million people, and I don't want to send for this specific product an SMS to everybody. So we're interested in the best 10%, who has the highest probability, and that can vary differently per model. That some model have a better area in the curve, but are not so good at the first 10%, and for the business that I work for, the marketing people are more interested in who are they performing in the best 10% than the rest, because we are not selecting these kind of people. You know?
Yeah, so there are a few techniques. The one that comes to mind, if you have a way to categorize the population, you can use something called stratified sampling, which basically takes the population and creates strata, and just you select a certain percentage from each of the strata that you've defined.
Because in the past I using SAS, and then my model comparison is to the different models is that the lift of the best 20%, this kind of stuff. Is that also possible here, or?
I think we're running a little short on time. Let me catch you after.
Yeah.
All right. Thank you very much, Myles.